This is Dr. Ramathilagam, Professor, Computer Science and Engineering Department, P.S.R. Engineering College, SIVAKASI. My lecture is about characterization of distributed systems. Networks of computers are everywhere. The internet is one as or the many networks of which it is composed. Mobile phone networks, corporate networks, factory networks, campus networks, home networks, in-car networks. All of these, both separately and in combination, share the essential characteristics that make them relevant subjects for study under the heading distributed system. Next, we are going to see the definition of a distributed system. A distributed system is one in which the components located at networked computers communicate and coordinate their actions only by passing the messages. Our definition of distributed systems has the following significant consequences. So there are three consequences: concurrency, no global clock, independent failures. We can see one by one. Concurrency. Concurrency means concurrent execution of the program. Next one, no global clock. When programs need to cooperate, they coordinate their actions only by exchanging messages. Close coordination often depends on a shared idea of the time at which the program's actions occur. But it turns out that there are limits to the accuracy with which the computers in the network can synchronize their clocks. There is no single global notion of the correct time. This is the direct consequence of the fact that the only communication is by sending messages through a network. Next one is independent failures. All computer systems can fail, and it is the responsibility of the system designers to plan for the consequences of possible failures. Distributed systems can fail in new ways. Faults in the network result in the isolation of the computers that are connected to it, but that doesn't mean that they stop running. In fact, the programs on them may not be able to detect whether the network has failed or has become unusually slow. Similarly, the failure of a computer or the unexpected termination of the program somewhere in the system is not immediately made known to the other components with which it communicates. Each component of the system can fail independently, leaving the others still running. Next, we are going to see the examples of distributed system. The first example is web search. The task of a web search engine is to index the entire contents of the World Wide Web, encompassing a wide range of information styles, including web pages and multimedia sources. Google, the market leader in web search technology, it has put significant effort into the design of a sophisticated distributed system infrastructure to support search. Highlights of this infrastructure include an underlying physical infrastructure consisting of very large numbers of networked computers located at data centers all around the world. A distributed file system designed to support very large files and heavily optimized for the style of usage required by search and other Google applications, especially reading from files at high and sustained rates. Next highlight is an associated structured distributed storage system that offers fast access to very large data sets. Next one is a lock service that offers distributed system functions such as distributed locking and agreement. The last one is a programming model that supports the management of very large parallel and distributed computations across the underlying physical infrastructure. The second example is massively multiplayer online games, that is MMOGs. Massively multiplayer online games, it offers an immersive experience where by very large numbers of users interact through the internet with a persistent virtual world. Leading examples of such games include Sony's EverQuest 2 and E-Online from the Finnish company CCP Games. The engineering of MMOGs represents a major challenge for distributed systems technologies, particularly because of the need for fast response times to preserve the user experience of the game. Other challenges include the real-time propagation of events to the many players and maintaining a consistent view of the shared world. This therefore provides an excellent example of the challenges facing modern distributed systems design. A number of solutions have been proposed for the design of this MMOGs. The largest online game, EVE Online, utilizes a client-server architecture where a single copy of the state of the world is maintained on a centralized server and it is accessed by client programs running on players' consoles or other devices. To support large numbers of clients, the server is a complex entity in its own right, consisting of a cluster architecture featuring hundreds of computer nodes. The goal is then to ensure the fast response through optimizing network protocols and ensuring a rapid response to incoming events. To support this, the load is partitioned by allocating individual star systems to particular computers within the cluster, with highly loaded star systems having their own dedicated computer and others sharing a computer. Other MMOGs adopt more distributed architectures where the universe is partitioned across a large number of servers that may also be geographically distributed. Users are then dynamically allocated a particular server based on current usage patterns and also the network delays to the server. This style of architecture, which is adopted by EverQuest, is naturally extensible by adding new servers. The next one is financial trading. Buying and selling of financial events carried out in two ways, via an exchange and over the counter. Distributed systems support for financial trading markets. E-communication and processing of items of interest known as events in distributed systems, with the need also to deliver events reliably and in a timely manner to potentially very large numbers of clients. Examples of such events include a drop in a share price, the release of the latest unemployment figures. This requires a very different style of underlying architecture from the styles mentioned above, for example, client server, and such systems typically employ what are known as distributed event-based systems. This figure shows an example of financial trading system. So the figure shows a series of event feeds coming into a given financial institution. Such event feeds share the following characteristics. Firstly, the sources are typically in a variety of formats such as Reuters market data events and FIX events. FIX means Financial Information Exchange Protocol, and indeed from different event technologies, thus illustrating the problem of heterogeneity as encountered in most distributed systems. The figure shows the use of adapters which translate heterogeneous formats into a common internal format. Secondly, the trading system must deal with a variety of event streams, all arriving at rapid rates and often requiring real-time processing to detect patterns that indicate trading opportunities. Complex event processing, which offers a way of composing event occurrences together into logical, temporal, or spatial patterns. This approach is primarily used to develop customized algorithmic trading strategies covering both buying and selling of stocks and shares, in particular looking for patterns that indicate a trading opportunity and then automatically responding by placing and managing orders.